Welcome back. Hopefully lunch was great. So after all of that core prod research from Facebook, the afternoon is all about the community. And we're going to kick things off with the cloud providers talking about how they're building tools and offering services to help developers on PyTorch, as well as the research community from academia and how they're applying PyTorch to solve problems in various domains. So enjoy the afternoon. Thanks.
Good afternoon, everybody. I'm Sunil Malia from AWS, part of the Machine Learning Lab team. I'm here to talk about how easy it is to build machine learning applications on AWS. At Amazon in general, we've had a long heritage of machine learning applications, right from search and recommendation engines to Alexa to now in store, where you can go pick up any shopping product and walk out without having to check out. So what are we trying to do at AWS as far as machine learning is concerned? We want to put machine learning in the hands of every developer and data scientist. There are tens of thousands of customers using machine learning on AWS and building machine learning applications. Every industry vertical is probably represented here in this slide. So I want to be more specific about how we think about machine learning and how it relates to especially PyTorch here today. So we think about machine learning in three different layers. So we have the application layer, where essentially we have computer vision, APIs as a service, speech, language, etc. And the bottom layer is the frameworks, where we actually make it easy for you to run any deep learning framework out there. We have machine images, which come prepackaged with CUDA drivers, MKL, all that is available. But we're going to focus on the platform for today. In particular, I'm going to talk about Amazon SageMaker. Amazon SageMaker, what we're trying to do here is we want you to focus on three aspects of machine learning. We want you to help make it easy for you to build, train, and deploy the models. So for enabling our customers and developers to build, we have a hosted notebook environment where within a few clicks you can actually get a Jupyter notebook that is provisioned. It has all the necessary packages. It's got a Conda environment, which has access to all the popular deep learning frameworks, including PyTorch, MXNet, TensorFlow, and Chainer. What's cool is it's actually, you can provision GPU instances. You can run it on a local mode, that is, run your code locally, and then run it in a distributed mode. And I'll talk a little bit about that. We also wanted to make it easy for people to run applications, not just deep learning workloads, but also traditional machine learning in a distributed manner. So we re-engineered some of the common algorithms, including we have object detection, text classification, or LDA, PCA. All these are available for you to use. Now, as I mentioned, we wanted to make it easier for you to run the popular deep learning frameworks, but also we wanted to be agnostic that if somebody has a particular framework or you've already got a code base, you can essentially containerize it using Docker and run it on the platform. So as I mentioned, there are algorithms that we built. For example, here you can use k-means. So we have inbuilt algorithms that are infinitely scalable. So we have benchmarks that are public as well. And they tend to do 10x better in terms of scaling when compared to the best alternative out today. All right. So I wanted to show how easy it is to use distributed or PyTorch and do distributed training. So as you can see here, we have a PyTorch container that's built. Right now, we have the pre-release, the preview container that's available. It's a nightly build. So all you need to do is package your code in this case, it's mnist.py, but you write your code, and then you pick the framework version. As you can see here, it's 1.0. And then you can pick your training instance. This could be just a CPU-based machine or GPU, which is available. So you just need to pick what you want to run on, and you pick the hyperparameters. Now, it's as easy. As you see here, if I wanted to run on more machines rather than 4 here, I can just update that and have 40 instances to do distributed training. So the heavy lifting is being done on the SageMaker side. As you see here, you can build your own algorithms as well, as long as it's, as I mentioned, you need to package it as a Docker container, and you should be able to run it. So streaming, here's the capability. We all understand that in order to distribute or be effective in distributed training, we want to have decoupled or stateless nodes. So by having sort of fixed memory, by streaming in data, it allows you to actually scale. And we have support for custom algorithms, which means you can leverage this for all the frameworks that are supported by SageMaker. But I think one of my favorite features is the automatic model tuning. I think we always spend a lot of time in trying to find what's that optimal model that we want to deploy in production. And SageMaker makes that easy by allowing you to do automatic model tuning. Now, I can specify whatever the hyperparameters are for my code. In this case, I've specified batch size, learning rate, epochs, and I can have a continuous parameter, categorical, whatever I choose. In this case, you can give a regex in specifying what you want to optimize on. I've specified validation accuracy. And then you can specify the max number of jobs and how many parallel instances. So it actually uses Bayesian optimization. So once you sort of get the results back, it tries to get to the best hyperparameter. What's great is once the job is done, you get a nice pandas data frame with all the parameters, all the results. So you can have a trade-off in between training time and whatever your accuracy metric or validation metric that you're looking at. So besides that, there's a hosting part where we want to make it easy for you to get your models into production. We understand that not every model that you produce may be directly applicable in production. So here, we actually enable you to A/B test. You can specify percentages in terms of traffic onto your model, and you use that to find out, and then you could have a dynamic switch between whichever model that performs the best. We also have a batch transform. So if you wanted to you have a massive data set that you want to run inference on, you can specify a batch job. It's essentially a script where you specify the necessary transformations that need to be done prior to doing the inference, and then post-inference hooks are provided. You package this up and pretty much use, again, as you probably see a trend here, the number of lines of code to launch some of these things is pretty few, right? Like 3 or 4 lines. So we want to make it easy for you to, once you have code, not necessarily worry too much about the infrastructure aspect or the platform aspect of running your models. So we have a lot of customers using Amazon SageMaker, but I think the key aspect that we focus on and try to improve on is we want to help you to get into production as soon as possible. So we want to reduce the idea time going from an idea to actually getting into production. And we've seen this successfully with Intuit as an example, where they've been able to reduce going into production from about 6 months to a week. So I encourage you guys to check out Amazon SageMaker. We have a GitHub resources and comprehensive documentation on our website. Thank you.
Hi, my name is Eric Boyd. I lead the AI platform team at Microsoft, and I wanted to talk to you a bit about some of the things we're doing with PyTorch at Microsoft and how you can really bring PyTorch into the cloud and use it really well that way. We've had a pretty great collaboration with the open source community. We worked a lot with Facebook and Amazon and others on things like PyTorch and on Onyx, and then expanding that into PyTorch. Last week we had Microsoft's big conference, Ignite, and we had Jerome come and present at the Microsoft presentation. And so, it's been a really great collaboration across the companies, and so we're really happy to just sort of see this area continue to push forward. So what I want to do is take a couple minutes and talk about, some of the different services that we have and really what we've done to make PyTorch easy and work really great across them. PyTorch has been a framework that has really taken off at Microsoft. We've seen lots of teams, really switching to it, and a lot of the work that we've done through Onyx and having, a great Onyx runtime and PyTorch's great integration with Onyx has made that really seamless. And so because we're doing it so much internally, and because we're doing it, so many of our customers are starting to ask for it, we're starting to build it into all of the different services and tools that we have. And so I'm going to talk a little bit about the various tools that we've got and go through in each of these in a little bit of detail, just to talk about, so how does this work? What can you do with it now? So it starts with the editor. If you're building machine learning software, if you're working in PyTorch, you're working in the editor. And VS Code is the #1 editor according to Stack Overflow. It's widely used. It works on Linux, on Mac, on Windows. And it's a really rich, great IDE. And has really great support. It's been around for a long time, and it's gotten great traction. It's open source, so if you want to change something about it, you can go download it and use it yourself. We've added a lot to it over the last really year even, focusing on adding much richer Python support. The Python community has just grown tremendously, driven both on the web serving side, the web dev side, as well as on the machine learning side. And so much richer Python support, adding all the things that you really would expect to see from your editor in there. All the things like autocomplete, IntelliSense, just making those just really easy to sort of get your work done and really have a fantastic editor that you can use. Deeper than that, we've recently added all the PyTorch documentation into it. So you can now be anywhere in your code, and you sort of find a function, and you can't remember the parameters. Instead of having to go to a web page and sort of look up, hey, how do I do this particular thing? You can just right-click, and the documentation shows up right in line. And so, really looking to make it simple and really make developers more productive when they're trying to use, the different tools that they have out there. And the last thing we have is VS Code Tools for AI. That's a plugin that you can add that makes it really easy to connect to cloud-based services, to train your models, all right from within the IDE, and just really simplify that process a lot. So just to sort of show it a little bit more, this is a screenshot of VS Code, and so it's a little bit small, but in the editor you can see someone's working through, and they've got the optimizer, the stochastic gradient descent optimized SGD, and if you forget the parameters on it, which is a very common thing, how does that which one's first and how do I set them up? Just being able to right-click right there in the code, have the documentation pop up, PyTorch documentation exactly laid out the way you'd expect it to be, just right in line and just keep you moving really quickly. And so developers internally love this, makes it really easy for them to get their work done. The next areas I want to talk about are just how, when you need to get started quickly, you want to start prototyping or you want to learn some things. So you can go to Azure Notebooks. Azure Notebooks is a Jupyter notebook and has PyTorch built right into it, already integrated and already installed, and has a whole library of PyTorch tutorials that you can go through. And so you can go and check that out. This is live now, notebooks.azure.com/PyTorch, and you can check out all the different ways, all the different things that PyTorch can do, and really a whole host of tutorials that will help you get up to speed and learn quicker. And then the next is the data science virtual machine. Sometimes you just need a VM, and you don't have to install all the different packages and configure it the right way. The data science VM comes with PyTorch already installed, all the things that you would need already installed, as well as a rich set of tutorials and libraries. And so really focusing on let's make people as productive as they can be, as quickly as they can be, and really drive that. The next area is Azure Machine Learning itself. So when you're ready to work on a sort of a larger project, I'm going to do multiple training runs. I want to keep track of my run history. I want to do some hyperparameter tuning. Then you're going to want to use Azure Machine Learning. Azure Machine Learning is a code-first approach. It's a Python-based SDK. You can pip install it, and from there you can go and call out to all the services on Azure. And so you can do everything from distributed learning. We have specific PyTorch-focused APIs that will really accelerate the distributed learning that you're trying to do in PyTorch. You can do hyperparameter tuning using Hyperdrive. I'll talk a little bit more about that in a minute. And then you can deploy your models, really simply if you need to deploy them to CPUs, to GPUs, to the edge. Really simple, straightforward methods for going and managing that. So let's take, there it goes. Sorry, I went too far. Let's go a little bit deeper into this. So this is just a Jupyter notebook showing you what you would do. And so if you have a PyTorch library, that sort of PyTorch file that you've written that builds your model, and what you want to do is start training it and iterating on it and actually trying to get it to converge to something that you can deploy to production. So what you want to do is you want to do an experiment. An experiment is just a trial run that you're going to run through a training batch. And so we make that really quite simple. You create just a PyTorch estimator, and here the source code is really nice and short, and it enables you to sort of pull in all the different things that you want. Here we're using 2 nodes that you want to train on with 1 process per node, making it really easy to scale to multiple nodes and to multiple processes. Using Horovod to distribute the parameters to it. So really makes it nice and simple to just go and run and train your job and get that iteration going. And then once you've run it, then you want to track and see how it's going. And so just sort of run, show the details from your run, get a nice sort of widget within Jupyter Notebook that'll show you exactly how it's performing and exactly how it's converging over time. And the next thing you're going to want to do with that is you're going to want to start tuning all the different hyperparameters to it. And so with Hyperdrive, this is a service that we offer that makes it really simple to go through and try all the different hyperparameters. But a naive approach is the grid search. It tries all of them. What we have behind this is a machine-learned model that is predicting what's going to be the best set of parameters based on your history, your data sets, the past runs that it's seen from other people. And the other thing that's really cool about it is that it watches the runs as they're going, and runs that look like they're not converging or not performing as well, it cuts off early. And so the amount of compute time that you spend could be a lot, right, if you're going to go through a grid search and try all of them or let all of them run tremendously. You can save a tremendous amount. This is used extensively internally. This came out of the Bing team where they were doing a ton of hyperparameter tuning and just really accelerated their development. And so we think this is really great. And also, drops right in. If you're using PyTorch, it's like 3 lines of code. You just add this in and get this going. And then finally, you've finished. You've got your PyTorch model. It works, and it does all the things that you want it to do. And now I want to deploy it. And so you can create a web service and about 6 lines of code that will deploy it. And now you have a model that you can go and call. Or you can create a container and put it any place you would like, on-prem in your application. All these things really focusing on making it as simple as we can. And so really, our goal is to make PyTorch a world-class framework. It's something that internally, teams are just eating up. The speed of development that you can get from it, the Achilles heel had always been, but the performance isn't good enough. But with Onyx support and then being able to have a fast Onyx runtime, we're getting fantastic Onyx support, fantastic performance as well. And so we see teams internally that have been using TensorFlow models for a long time really switching wholeheartedly and saying PyTorch is is faster, it's better, it's easier, and so we just want to see that continue. We're big fans of this community and partner very closely with it and really want to see it continue to move forward. We're seeing customers use it too. Accenture is a customer of ours. When we talk to any customer and they're like, tell us what should we do for our deep learning? If they don't know what they're doing, we always push them towards PyTorch. We think this is the easiest, fastest way for them to get unlocked and to get onboarded. And so Accenture's done a whole bunch with this, and a whole bunch of customers have come through. And so we're really excited about how this community is growing and the work that we can do together. And so I've spent a bunch of time talking about how we've made PyTorch work at Microsoft. I'd like to invite Ewan out to talk about some of the things we're doing just to make PyTorch better all on its own. So Ewan?
Hello, hi. I'm Yuan Yu. I'm an architect of on the Microsoft AI framework team. So what I'm going to talk about, as we just learned from Eric's presentation, so we are actually doing a lot of work to make PyTorch great on Azure. And obviously, we are also interested in making PyTorch great for everyone. So in the next few minutes, I'm going to talk briefly about our PyTorch investment. And the first thing is we actually formed a dedicated team, a PyTorch team, and working on PyTorch. And we work very closely with the PyTorch community, developer community, and also will contribute any good things into the PyTorch GitHub repo. And obviously, we also want to address all the needs of the Microsoft customers. So here is a list of the initial priority for the team. So first, we want to build a very good Windows release. So that means that it's going to be full parity with Linux in terms of the performance and also functionality. And so the second thing is we want to work very hard to scale the PyTorch training. And the third thing is operationalize the PyTorch model in production. So I'll briefly talk about the second or the third. And so we look at the PyTorch, and so one thing which is very interesting to us is the data reader. And so obviously everyone knows the data reader is actually very important as part of the training performance. So what we want to do is we want to first improve the existing PyTorch readers and to make it high performance. And also we plan to add new PyTorch readers and to deal with these two kinds of data formats, and the HDK and also the Azure Blob. And that's a little bit longer term, so we also want to improve the distributed training. So one part is the team has been working very closely with the Microsoft Research and to get the Microsoft Research's innovations into PyTorch. And also we want to port some of the good CNTK training algorithms, things like 1-bit SGD and also block momentum into PyTorch. So the second focus for the team is actually to make sure the PyTorch can be operationalized in production. So first, we'll focus on PyTorch to Onyx export. That means we want to make sure to increase the Onyx operator coverage. So therefore, we reduce the dependencies on the custom ops. And the second thing is we want to make sure all the PyTorch models can be exported to Onyx and run on Microsoft Onyx runtime. So which is an Onyx runtime that runs on in the cloud and also on all kinds of devices Microsoft care about. And a little bit more speculatively, we are going to engage with the Facebook team to work on better solutions for dynamic models. So to recap, what we have been doing so far is we have integrated PyTorch in every Microsoft machine learning product. So here is the list of things which is given in Eric's talk, and feel free to please give it a try and see how great it is. Thank you.
Hey, everyone. Thank you so much for the opportunity to come here and talk about the ways that we're working to make PyTorch a first-class and best run on Google Cloud. I know I talk really fast, and I've had a lot of coffee, and I know everyone's in their post-donut coma, but I promise there's a ton of stuff here, and I'm really excited to be here. So Google has recently become an AI-first company. Almost every single product at Google is touched by AI in some way. And literally thousands and thousands of new models are being checked in every year to make our products better and address our customer needs more. But the reality is that as excited as I am about the advancements we're making in AI, it's a fundamental technology that we truly believe will affect every customer in the world and will help make all of their products and their scenarios much, much better. And so our mission at Google Cloud is to democratize AI by making it easy, fast, and useful for everyone, no matter what their skill set. And the way that we're doing that on Google Cloud is really with three big investments. The first is we are opening up our hardware and our data centers, which are really designed to be machine learning friendly and cloud native. Second, we're making big investments in easy to use, easy to get started. And third, we're integrating with a number of different open source frameworks to let people use the things that they're already familiar with in order to use, under the hood, basically use the best of breed with Google Cloud. So let me touch on these three things very briefly. The first is Google Cloud is really designed for machine learning infrastructure. The most fundamental advancements in the past 10 years have been driven by the use of specialized hardware. And Google's infrastructure is optimized for running this cloud-native machine learning workloads. For example, the latest hardware advancements are already available on Google Cloud. All major GPUs are available today, with T-Force coming soon. We have NVLink available. We have local SSDs for fast disk. And of course, we do have custom accelerators, including multiple generations of cloud TPUs and TPU pods. I'll touch on those in a second. The second is around flexible infrastructure. Google Cloud is designed to allow you to use machines that make sense for you rather than the cloud that you're running on. We offer custom machine types to allow you to arbitrarily assign numbers of cores, up to 160 cores, and arbitrary amounts of RAM, up to 4 terabytes of RAM with 8 GPUs attached to each machine. And our ultimate goal is to give you sizes and shapes of machines that let you build your models in the way that makes sense to you, saving the up to 45% of spend on cloud that is wasted today. And even better, we offer preemptible VMs and auto-scaling node pools, which means you can scale up and scale down based on when your job is running, rather than having to write your own scheduler to handle that. And finally, we offer scale. 0 to thousands of cores and GPUs. We offer cloud TPU pods, and it's all connected by Google's private backbone infrastructure. But don't just listen to me when it comes to scale. Here you have an example from OpenAI running a very, very large reinforcement job up to 100,000 preemptible cores with 1,000 GPUs attached in order to advance their very large reinforcement learning in partnership with Google engineers. So that's the infrastructure, but it only matters if people can actually use it. There's a lot of stuff to talk about here, but I'll just touch on our brand new deep learning VM images, which have PyTorch 1.0 preview built in. Now, with one click, you can get an entire machine learning environment with all the necessary drivers and tooling and frameworks built in for you to get going. And third, we're dedicated to be flexible and hybrid ready. The reality is that Every enterprise is multi-cloud in some way. Over 80% of enterprises today are using multiple clouds, whether or not those are laptops, on-prem, or your particular cloud. And they're not just using one of those environments, they're using up to 5. We want to help by bringing our software and our technology to where you are. Recently, in December of 2017, we launched the Kubeflow project. That's an out-of-the-box way to run machine learning platforms on Kubernetes. And it takes advantage of all the native integrations that Kubernetes offers. So if it's running on your laptop using something like Minikube, you can use local GPUs and CPUs in that way. If you're running on the cloud, you can do it distributed. You can use native TPUs, GPUs, whatever that cloud has available for you. And to show you, we already have PyTorch enabled and show you how easy it is. I'm going to actually walk through a full installation of a PyTorch platform running on Kubeflow. The first is you execute these 3 commands. This sets up your entire Kubeflow environment. Again, wherever Kubernetes is running, you can execute these commands. Second, I execute 2 more commands to install the PyTorch packages for training. And then finally, we install a server for doing inference. In this case, we're demonstrating the brand new NVIDIA inference server contributed by the NVIDIA project, or by NVIDIA to the Kubeflow project, where you can run an entire model inside your Kubeflow deployment to do inference using PyTorch. This is all it takes. Literally these commands, there's nothing hidden here, and it runs everywhere Kubernetes runs. Second, we are also making investments in other open source projects. For example, we've heard from the community that PyTorch users want to use all the flexibility and visibility that TensorBoard provides. And I'm proud to announce today that the TensorBoard and PyTorch team are collaborating to make PyTorch use of TensorBoard much, much easier. Thank you. All right, so that's a bunch of cool stuff. I only have 3 pillars. What's this doing here? Let's get to the elephant in the room, cloud TPUs. Google's been investing in TPUs for years. They're tensor processing units. As you may have heard, they are very, very fast, and they're dedicated to running machine learning workloads in an extremely cost-efficient way. And these weren't just options for Google to go and invest in. We had to. As Jeff Dean likes to say, we literally would have had to build additional data centers in order to have all the machine learning that we want to offer to our customers. The TPUs have made extremely fast progress. TPUs v1.0 in 2015 came out, 92 teraflops, only inference at the time. V2 came out in 2017, 180 teraflops. And V3 we were proud to announce at Google Cloud Next just a few months ago, 420 teraflops and doubling the amount of RAM, allowing customers to run even larger models than before. And those aren't just individual chips. Inside Google Cloud data centers, you're able to run them as TPU pods, meaning they are connected via many, many hosts with very, very fast interconnect. And it means you can program against an entire array of these TPU chips as though they were a single machine. Think of it as a supercomputer in a box. TPU pod V2 is 11.5 petaflops, and V3, which we had just announced, is over 100 petaflops. This is literally one of the fastest supercomputers in the world. To show you what this actually means, all this performance, with a TPU running against a very standard workflow, ResNet 50, you're able to process 4,100 images per second, get to 93% accuracy, and using those preemptible VMs I mentioned earlier at just $11 in training cost. And it scales all the way up. Without changing anything about your code or the way you deploy, if you take that exact same deployment, that exact same ResNet, and push it to TPU pod, you'll have to change your hyperparameters, but other than that, you're able to get to 219,000 images per second, same level of accuracy, under 9 minutes in training time. So, TPUs, yes. We are proud to announce today that collaboration is already underway. We have a prototype of ResNet 50 running against TPUs with PyTorch. We're planning to open source this, and we continue to want to expand into the community and collaborate with everyone. Please email us here. We would love to work with you right now when it comes to new workloads coming online. And with that, I would like to say congratulations to PyTorch on 1.0. It is an enormous achievement. We couldn't be more impressed with it. And thank you very much.
Thanks, Dave. That was amazing. Yeah, it's been hard to hold back that news. OK, we're going to switch over to the academic track now. So starting with Anima Nayankumar from Caltech.
Thank you, Joe Spizak, and the others from the PyTorch team for inviting me. I overlapped with Joe back at AWS, and we had a great time working together.
Good job, Dave.
So being both in academia and industry, really has helped me look at a large array of problems that arise in industry, but so far haven't received that much attention. Because when it comes to AI and machine learning, there are really three pillars, right? There is the data, there are the algorithms, and then there's the compute infrastructure. So most of the time we spend in academia is on algorithms. How can I get the best algorithm? What kind of bound does this have? What kind of sample complexity? What kind of computational complexity? What are the problem instances it's going to solve? But then in industry, there is so much more that we are faced with. Most of the time we don't have data. How do I get labeled data? And there is so much noise in that process. I'm training on one data set and then have to serve on another. How do I deal with this? And then I have to scale this up on large-scale infrastructure. And what are the challenges involved there? And it's so critical to have open source software frameworks like PyTorch to really enable us to realize the algorithms, right? So this is, to me, the beginning of how academic research and industry research really has to come even closer to one another and tackle problems together. So now I'll give some snippets of applied research we've done, both at Caltech and during my time at AWS. And towards the end, I'll also talk about our initiatives at NVIDIA. So one of the challenges in scaling up machine learning is how do I do distributed training? So if I have too much data to not be able to train in one machine or one processor, I would need to distribute it to multiple ones. So the simplest form of parallelism is the data parallelism. I'm going to distribute my data set in equal amounts to different processors, right? But what this means is if they're doing local computations, there has to be communication between them. And this is a big challenge when it comes to scaling up machine learning. There will come a point where communication costs will overwhelm computation costs, and thus you've hit a limit on how much you can scale. So how do we resolve this? So we came from this more algorithmic perspective and asked, can we do better than the standard optimization algorithms? The standard is the stochastic gradient descent. Instead, can we do a compressed version of it? So the workers, typically the GPUs, would compute the stochastic gradients, but compress them when they send to a server. So in this architecture, there's a parameter server that takes in the compressed gradients and then aggregates and sends back the compressed answer. Right? So, and we looked at the very simplest form of compression, which is just to send the sign of each coordinate. So you send the signs to the parameter server, and what the parameter server does is to do a majority rule and sends it back. So in contrast, if it was stochastic gradient descent, you were doing averaging, right? So on both the sides, there is like a 32x savings in how many bits you send. So this is great. I mean, there is communication savings, but then how well does this do? So what we found in our recent experiments was that you have almost no loss in accuracy. So on Resonance 50 on ImageNet, we see that yeah, the test accuracy, both at like 7 workers and 15 workers, you have almost the same accuracy in the end. But when you look at the time, when you look at the throughput, right, you get a gain with SignSGD. So at 7 workers, it's about 30%. At 15 workers, it's about 25%. So you can have now lower communication costs and still not lose in terms of accuracy. And in fact, across other architectures, we've seen a lot of promise. For instance, for language tasks, the QRNN, we found even a bigger speed up in terms of communication compared to nickel. So by the way, all these benchmarks were comparing to nickel that recently got open source from NVIDIA. And so it turns out this SignSGD is also Byzantine fault tolerant. So intuitively, if you're doing just stochastic gradient descent, one machine or one processor can have a large influence, and hence, if it is adversarial, it can really mess up the results. But if you're only sending the sign, that's not possible. And so with our analysis, what we show is it's possible to be as much as 49%, Byzantine fault tolerant. And in experiments as well, we find that even with the proportion of adversaries, changing, you still have, you're going to lose some accuracy, but you're still able to tolerate them. And we have results in the paper showing how you can, it's much better than what stochastic gradient is able to do. So here I didn't talk about the theory, but it turns out that there is a lot we can also say about in theory. We can establish convergence rate bounds for SignSGD and show that, in fact, there are regimes where this is faster. Training is faster with SignSGD than stochastic gradient descent. And I didn't show the training loss. It turns out that's also the case in experiments. And so the conditions we assume in theory, we can also verify them. These are conditions on signal-to-noise ratio and other natural assumptions. So there is really a nice kind of closing of the gap between theory and practice here. And I hope to see more of such results in future. So the PyTorch code is now available. I encourage you to go and take a look. And Jeremy and Jave are here, so they'll also be presenting the poster. So feel free to talk to them more. Another area that I've worked on has been tensors. How we can take linear algebra and matrices to higher dimensions. With everything, the docs are great to explain a concept, and here you have for tensors as well. And so what are really tensors useful for? If you have lots of dimensions in data, right, like tensors are natural. But tensors are also natural if you have higher order correlations in your data. And you can really expand upon matrix operations to higher dimensions and use the notions of tensor contractions. So Tensorly is this high-level API that Jean Kosafi has built. He'll be also presenting a poster on that, which makes it very easy to use these tensor computations, different forms of tensor algorithms, with any backend. And there is extensive support for PyTorch. There are lots of PyTorch notebooks available that Jean and others have built, so I encourage you to go and check them out. And one architecture we've explored is this tensorized neural network, where you can do tensor contractions and tensor regressions. And it turns out that you can get a lot of space savings without loss in accuracy. So these tensorized architectures can lead to more compact neural network architectures. So the last snippet I want to give is looking at how we can use learning to control and learning in robotics. We have this new center at Caltech called CAST, which I'm very excited about because it's really bringing these different disciplines together. And so there we are looking how we can have better landing of drones. So this current video is without any learning. This is like the standard baseline control algorithm, the PD controller. So instead, we asked, if we used a neural network to learn a ground effect model and correct in terms of a residual, how does the landing improve? And so you can see here that it's able to land much quicker. So, and it turns out that actually, if you just used a plain neural network, this is not enough. You need like this notion of spectral normalization, and that's also gives you nice theoretical guarantees on stability. And so this is really the first, foray for me into control, but I see a lot of problems that can use learning. And this was also built on PyTorch, and we'll release the code. And so CAST has also this unique facility where there is a wind tunnel, rather a wind testing facility. And so this array you see is all like programmable fans. So you can have like any kinds of wind vortices, and you can also put it down and make it into a landing one. I guess I didn't choose the video with wind. I apologize. There was another one with wind. You can believe me on that. But anyway, we are really excited about this facility. Yeah, so there's been a number of works in addition to what I presented that's really trying to bridge theory and practice. We've worked on the data problem in terms of how to improve data efficiency through active learning, through semi-supervised learning, generative modeling. There is also work on the infrastructure side, as I said, TensorFlow and other software frameworks to really push that into practice. And at the same time, theoretically, how we can come up with more natural assumptions of that mirror what occurs in practice and really bridge this gap. And now at NVIDIA, I just started. It's been 2 weeks, so it's a new adventure. And I'm looking forward to growing machine learning research there. There is a rich history of research in so many areas, and we're growing in machine learning. So feel free to reach out to me if you want to know more. Thank you.
Hello, my name is Alexey Efros. I'm from UC Berkeley, and I'm very happy to be invited to this party. My group will love PyTorch, and so I'm going to tell you a little bit about something a little bit more frivolous than curves and graphs. Pixels. So you know that the standard why deep networks are great. They take very high-dimensional image data, noisy, complicated, and they produce a nice low-dimensional label. Okay? But what if we want to produce something that is also nasty and high-dimensional, like another image? So we want image in, image out. So it turns out this is actually not a very easy problem to do, because you think of something like, okay, we just stretch the last layer and go for it. That doesn't quite work. In fact, that's what we tried. We thought, OK, let's do something very simple. Let's do colorization. Grayscale image in, color out, and then we can do fun things. We can colorize images, right? Very simple, right? It's basically a regression problem. Why not? Just let's do a regression. Here's linear regression, L2, and it doesn't work at all. And it doesn't work. It's all very kind of sepia color. It's not very colorful, right, compared to the ground truth, right? So what happens? Well, the problem is that if you have a multimodal distribution, for example, so you have this bird that might be blue, or it might be reddish, right? So what is L2 going to do? Anyone? Take the average, right? And average in color space is great. So that's why you get all these nasty gray results. So this is not the right loss function. Instead, we had to worry hard and figure out, OK, we can do maybe make it a classification and maybe boost kind of enhance the rare colors, and then we get something like this that is different from the ground truth, but also kind of nice and colorful. But sometimes when you try to make something more colorful, sometimes you overshoot, right? You write your loss function by hand, and you get something like this, which is just too much. So really what we want is we want some kind of like a universal loss function that, for any kind of image-to-image problems, it will look at your image and say, this looks good, right? And we have this loss function. I have it. It's called graduate students, right? It's the graduate student descent. It's beautiful. They keep hacking until it looks great. and then we send it off for a conference, right? But it's kind of expensive, and it takes a long time. Another thing we can do, and in fact that's what we did for the caller work, is you have a whole bunch of real images, and so we actually go to Amazon Mechanical Turk and present our results and present real images, and we say, which one looks real? And if the Turkers are a chance, then we say, OK, our algorithm is doing well. But it's kind of not easy to backprop through a Mechanical Turk, right? It's very, very expensive. So what do? Well, luckily for us, around that time, Ian Goodfellow came up with this wonderful work, generative adversarial networks, that basically replaces the Turkers with another network, right? And the network, as hopefully most of you know, is basically it's a classifier that is going to classify whether it's a real image or a fake image, okay? And then you can backprop through that, and great things happen. So you have your generator, and then on top of that you put a discriminator, and the descriptor does, the generator basically tries to synthesize fake images that fool D, and D tries to identify the fakes. Makes sense, right? One way that we like to think about it, which is kind of a little bit different, is that really, if you think about this in this kind of conditional case, the discriminator is kind of like a loss function, right? It's a learned loss function. From G's perspective, D is basically a loss function that tells you, what do I need to do to make it look real, right? And the nice thing is it's learned, it's trained, and you can basically, for any task, you just train a new one, and it will just work well. And this is really where we started switching to Torch and later to PyTorch, because our previous framework just couldn't deal with this kind of optimization. So we had to switch, and we've been happy ever since. And then now you train in grayscale to color, and it works. You give it Google Maps and train and ask it to produce satellite images. No problem. It's not as good as ground truth, but it's pretty good. You can go the other way around. And it's all exactly the same code, the same parameters. Everything is exactly the same. You just train it on different data. You can go from labels to facades, something like this. You can go from day to night, exactly the same code. You can go thermal to RGB. It's kind of magical. I didn't really realize how it can do it, but whatever. We can go from edges to images. And we can train on that, and then we can actually give sketches, like kids' sketches, and see what it can do with sketches, and it actually still does pretty well, surprisingly. And so we released the code on GitHub, and it's really amazing how people just started using it, and not just computer science people, but like just lay people, even artists. So people created these edges to cats app, and started using it. You're welcome to try it. But then, kind of more exciting for me is that like real artists started downloading this thing, getting themselves GPUs, and doing something that we really just never thought of would be possible. Some really cool stuff. And I'll just play you a little bit of this, one of my favorite ones. This is real time, just pix to pix, and a lot of imagination. This is a very nice artist. Google him and to see more of his stuff. So I think this was trained on a whole bunch of seascapes.
With flowers in my arms, for the dream I'd created. I waited till dreams like my heart were all broken. The flowers were all dead, and the words were unspoken.
Anyway, you can watch it later. Another thing we thought we could do is now we can also plug in other tools that our computer vision has gotten better at. For example, pose detection. So given an image, OpenPose and other programs like that can produce a pose for it, and it's actually working pretty robustly now. It's very nice. And now we can use those as inputs to our pix-to-pix, image-to-image translator just like before, just chain it together. And now what we can do is we can transfer, kind of do a do-as-I-do motion transfer, given a professional, transfer that to an amateur. And here is some examples of that. Everybody loves subject number 2. This is Ting Hui Zhou. His PyTorch coding is much better than his dancing. Okay. So now, if you have paired data, then it's, we know how to do this. What if you have unpaired data? What if you have something like you have a whole bunch of horses, you have a whole bunch of zebras, you want to translate horses into zebras? Kind of crazy, but why not, right? So what we can do here, we don't have correspondences, but what we can do is we take adversarial network idea and we combine it with what we call cycle consistency. Think about it as like in language. Let's say that you want to write a letter in French and you only speak English. So what you do is you translate into French using Google Translate, and then to make sure that it's correct, you translate it back into English and see that it actually is the same thing. So it's basically the same thing we are doing here. We take a horse, translate it into a zebra, only with the adversarial loss that it needs to be in the class of zebras. Then we translate it back, and then here is the cycle consistency loss. Basically, we need to say it should be pretty much what we started with is what we should end with. Okay? And then we do it the other way around. And so you can change horses into zebras, and you can even do it on video. Check out the tail. You can do oranges to apples and back. You can do photos to Cézanne paintings. You can do paintings back to photos. You can, kind of collection style transfer, change of season. Again, the same code. Everything's online. We can do CG to real, and more weirdly, real to CG. You can kind of wear it and see, like, wow, this is like my life as a computer game. And even the failure cases are kind of fun. So finally, of course, all of this work is done by my wonderful grad students and postdocs, and they're fantastic, and they all love PyTorch. And so I asked them, why do you love PyTorch? And so I got a whole bunch of responses. Everybody is excited about the ease of prototyping and dynamic compilation graphs and this and this. I love this, NumPy with GPUs. But for me, really, the reason I love PyTorch is that it allows my students to be more creative, because you can do things really fast and you can see the results right away. And I think that's the coolest thing for us as researchers. That's why we like PyTorch. Thank you very much.
Hello, I'm Andrew Wilson, and with Jake Gardner, I'll be presenting on optimization and scalable Gaussian processes in PyTorch. So I'm a professor at Cornell University. My group works in a number of areas, including probabilistic deep learning, scientific computing, scalable Gaussian processes, kernel learning, optimization, training of deep neural nets, and we're excited about all sorts of different applications: vision, NLP, spatial statistics, BayesOpt, public policy, public health. And almost as a lab policy, we release software for essentially all of our projects. I strongly believe in open and reproducible research. A lot of these projects are available at the URL at the bottom of the slide, and increasingly, a lot of our code is in PyTorch. We've found that PyTorch has been really excellent for prototyping models, for research development in general. So the first of the projects that I'm going to discuss today is called stochastic weight averaging, which is an approach we've developed for training neural networks. The basic idea is extremely simple. Just basically run SGD, but with a modified learning rate schedule, either a high constant learning rate or a cyclical rate, and maintain a running average of the parameters traversed by SGD during training, and use that instead of, say, the final converge point with a regular schedule. And when you do that, you see quite significantly improved generalization. The reason for that, as we've discussed in a recent paper at UAI, is that this procedure tends to converge to much flatter regions of the training loss. And so this makes it quite robust to the shifts that we often see between the training and test loss, as I've shown in the figure on this slide. For that same reason, this approach is also very robust to low precision computation. So it works extremely well for training in low precision, which harmonizes beautifully with a lot of the work that's been discussed today about using PyTorch for low precision training. This method is now available in the new PyTorch contrib, and using it is as easy as just calling torch.optim.swa. Scalable Gaussian processes has also been a very active area of research within my group. So if you're not familiar with GPs, don't worry. They're very kind of elegant models for distributions over functions with properties that can be controlled very intuitively using kernels. And they provide very natural representations of uncertainty, and they have applications for almost any predictive task. But their main kind of limitation has been computational tractability. And so a lot of the work that we've developed has enabled Gaussian processes to be now applied on problems with, say, millions of training points instead of thousands of points, and with very flexible kernels that can automatically discover a lot of interesting statistical structure in data. Our approach is grounded often on constructing fast approximations to matrices, which will enable fast matrix vector multiplies, and this harmonizes very beautifully with GPU acceleration. And in fact, a lot of this work has been developed as part of our new package called GPyTorch, so Scalable Gaussian Processes in PyTorch. And the heart of this package really is an inference engine that enables really fast linear algebra operations. So even if you don't use or don't care about Gaussian processes, you can use this package to get very quick solutions to linear systems, fast log determinants, square roots of matrices times vectors, all sorts of things that you would want to use for quite a variety of models very efficiently. This is a team effort, so it involves Jake Gardner, Jeff Pleiss, Killian Weinberger, myself, and a number of significant contributors, including Eitan Bakshi and his team, Max Ballendat and others. Both Jake Gardner and Jeff Pleiss are here at the DevCon, and Jake is now going to tell us more about GPyTorch.
All right. Hi, I'm Jake. I'm a postdoc at Cornell. I work with Andrew and Jeff, who's here, and also Killian. And I'm going to be talking about GPyTorch, which is our implementation of Gaussian processes in PyTorch. And it's going active in beta today. So I think we just pushed that to master, and you can now just install it with pip install GPyTorch, and it's great. So GPyTorch has a number of features compared to other GP implementations that I'm really excited to share today. Probably the most important of these is that it's really, really fast. So compared to existing packages, even ones that support GPU computing, we're often up to 30 times faster, even just for exact Gaussian processes. So nothing scalable or interesting going on. It's just the way we do inference. But on top of that, we've also done some exciting work that appeared at AI Stats and ICML. And that's going to be, that lets you get predictions up to even 1,000 times faster, and lets you do things like sampling even up to 18,000 times faster in certain cases. GPyTorch is fully modular, so everything we implemented is sort of implemented as PyTorch modules. And what that lets you do is do things like deep kernel learning, where you can combine neural networks and Gaussian processes together very naturally. Putting a Gaussian process in GPyTorch on top of a neural network only incurs about a 20 to 30% overhead over the full neural network. You get comparable accuracy, but you also get the uncertainty estimates that Gaussian processes are sort of so well known for. And finally, it's very easy to implement models in. So instead of providing very core built models ahead of time that you can sort of pick and choose from, what we do instead is we sort of give you the tools to implement any complex model you might like, for example, deep kernel learning. So at the heart of GPyTorch, we do something fairly different than many other packages in the way that we actually implement our inference method. And we call this sort of black box linear algebra, and it's based on tools from scientific computing and numerical linear algebra that are very popular today. And the idea is, if you take a matrix and you give me just a routine to do a matrix vector multiply with that, then there's methods in numerical linear algebra that do all sorts of interesting things. So for example, I can do linear solves, just given an MVM. I can do things like least squares problems. I can also do things like log determinants and eigenvalue decompositions. I can do SVD. I can do trace. And I can do all of this just with access to a matrix vector multiply. And this is sort of the main feature that underlies GPyTorch and how we actually get at all of these operations, which are the things you actually need to do GPs. And in order to sort of build this framework around this MVM approach, we actually introduced this concept that kind of builds on the torch tensor, which we call the lazy tensor. So a lazy tensor is everything like a tensor. So a tensor in Torch is just a matrix. And a lazy tensor is like a tensor, it's just a little lazier. And so the way you implement a lazy tensor is you extend lazy tensor and you define a matmul, and that's all you define. And then we define all these other interesting functions you might want to use with a lazy tensor. And then what's cool about that is they're closed under certain operations that we know about ahead of time. So for example, the sum of two lazy tensors is a lazy tensor because matrix vector multiplication distributes over addition. The same thing is true of the product of lazy tensors and the Kronecker product of lazy tensors, and all of these things can compose in nice ways. And what that means is you can write code that kind of looks like this. It looks exactly like what you might write in standard Torch, but the difference is at the end, it's still a lazy tensor that's just recorded what you wanted to do. And only when you actually call one of these interesting functions do we actually then take the matmul that we can build for you and actually do that efficiently. So why would we even do this, or where does this become interesting? Well, the main place this becomes interesting is when you have structured matrices. So for example, if instead of just a normal matrix that I know nothing about, I know my matrix is low rank, then all of a sudden, I can do a matrix vector multiply in n r time instead of the traditional n squared time, where r is the rank of the matrix. There's other kinds of structured matrices that are interesting. For example, Toeplitz matrices, which look very whimsical, but they're basically these matrices that have constant diagonals. So everywhere the color is the same, have the same entry. And I can do matrix vector multiplies in n log n time with those. And in fact, matrices like these are sort of the same kinds of matrices that are used to do convolutions a lot of the time in neural networks. And of course, a traditional example of this is just a sparse tensor, right? So if I have s non-zero entries in my matrix, then I can do a matrix vector multiply in order s time. So now this is sort of how we build these scalable GP methods, is we approximate these matrices using some set of structured matrices, and then we figure out what the running time of just an MVM is, and that ends up being the running time of the full GP model. So we implement lots of things with this, lots of standard methods that people have worked on in the past for scalable GP methods. So for example, we obviously implement exact GPs. We implement this technique SGPR, which is very popular. And we also implement SKI with deep kernel learning. And in most of these cases, we get orders of magnitude speed up or better. But we also use these kind of insights and these MVM-based ideas to get even faster methods. So for example, we recently published a paper at AI Stats where now on these very large data sets like protein here, you can actually train in 30 seconds instead of maybe 20 minutes, for example. And we also reduce in an ICML paper the time required for prediction using some of these ideas down to constant. And so what that means is as your data set size grows, we actually get upwards of 1,000 times speed up in the prediction time, which now means you can take your deep kernel learning model or whatever have you, and you can actually make predictions in time that seems reasonable. Yeah, so that's all I've got. So thanks.
All right, hi everyone. I'm Zico Coulter. I am a faculty member at Carnegie Mellon University. I'm also a chief scientist of AI research at the Bosch Center for AI. And what I want to talk about today is complex differentiable layers in deep learning. And I realize sitting back there, that might be a little confusing. I mean complex here as in just complicated, not as anything about the imaginary numbers. So I want to talk about what I mean by that. So let's say you wanted to build something like a self-driving car. I actually did used to work on that particular self-driving car. There's many people that are much more up to date on this than I am now, but I think it's still a good thought exercise to think about. So if you want to do what we sort of think of as deep learning for a self-driving car, you kind of think about something like this, right? It takes sensor inputs, feeds it through a bunch of convolutions, followed by element-wise nonlinear operators, and eventually out the other side comes out steering and brake commands, and your car drives this way. So I don't know of anyone, maybe Andre would advocate for this. I don't know of anyone that would really advocate for this fully. I think it sounds kind of crazy to do this when you put it this way, right? Why would we ever trust a self-driving car based upon a bunch of convolutions and nonlinear operators? What people actually do in practice, of course, something more like this, right? What they really do is something like what we think of as kind of traditional programming, right? Where you take your sensors, you feed it into a state estimator, and you feed that into a dynamics model and a cost function, and you combine that together to form a planner, forms a trajectory for the car. You feed into a controller that plans a path for the car, or a sequence of controls to achieve that, and that eventually becomes your set of actual inputs to your actuators. Right? And this is how, I should say, every self-driving car platform I'm aware of uses that thing on the right now. That's how we actually build software. Because when it comes down to it, if the pure deep learning model doesn't work, how do you debug that? How do you go in to expect that and see what's working, what's not working? Whereas, of course, we have this known modularity, this sort of debugability of the model on the right here. So what my group is looking at, or one of the things we're looking at, basically boils down to how do we combine the benefits of deep learning. Well, I should say combine the benefits first of traditional programming. So this includes things like debugability, modularity, explainability, with the benefits of deep learning. And the chief benefit, I think, of deep learning really comes from the end-to-end training and self-improvement via end-to-end training. So how do we combine those two things? It's really a large goal of my research group at CMU. So to talk about that, let me dive a little bit deeper into this. Let's talk about a model like this. And I want to look at one of these modules. I want to look at the planner module. And the way these planner modules can work, not always, but what they can work, is actually by solving an optimization problem. All right, so the planner, what it does is it determines a set of actions. Those are the U there in this notation, and states, that's the X here, that minimize some sum of costs over some horizon, subject to the fact that I have to start in my initial state, right? I can't jump around from my first state. And the state evolves according to some dynamics there. So F here is the dynamics model for the system. And the controls have to be in some feasible set, right? Now, it turns out this paradigm of optimization is a really powerful one. You can phrase a lot of modules we develop essentially as their output is the solution to some optimization problem, which depends on the inputs to that layer. Right? This is how we define a lot of different modules, kind of in traditional programming. And so what we've done is we've developed the tools to embed things like this into deep networks. So we've developed the most basic of which we call the OptNet layer. But this is a layer in a deep network that solves an optimization problem. In particular, this one here solves a quadratic program. It's a particular type of optimization problem that involves basically a quadratic objective subject to linear constraints. But the idea here is we're building a layer where the output of that layer is the solution to a quadratic program, where the program then is set up as a sum function of the input to that layer. All right, this is a really generic but powerful operator. And it's one that also, I won't mention this, but it does happen to actually generalize a lot of the linear and nonlinear operators we're familiar with, like just matrix multiplies, of course, but also things like ReLUs and stuff like that can all be actually formulated in this framework here. So it actually is kind of a strict generalization of a lot of things we're familiar with, but of course with even more power than that. So the question, of course, is if I want to have a layer like this, if I want to have a layer that basically, as outputs the solution to an optimization problem, and I'll talk about some applications in a second, but just thinking about it kind of qualitatively for now, how do I do this? How do I, in particular, differentiate through a layer like this? I'm not going to show it in too much detail, but sort of the question here is if I have some layer here, for example, where my output of my layer Z is a argmin, it's the minimization, it's the solution to some quadratic program. Now say I want to differentiate that whole thing with respect to, I don't know, the right-hand side of the inequality constraints of my quadratic program. How would you do that? And this is where, we did work out the math for this. It's not too hard. You basically differentiate some conditions that specify the solution to this problem. But the thing that I actually want to emphasize here is just how easy libraries like PyTorch made this back in the day when we were first doing it. So back in the day, I think a lot of libraries can do this now, but back in the day when we were first developing this, Brandon and I, there weren't a lot of tools that let us do this. And the wonderful thing about sort of PyTorch libraries, they let us basically write this layer. Here it's all kind of set up here except for that QP function call there. But what we can do with PyTorch is basically make this kind of layer more or less seamless to people that want to use it. Right? So if you want to use a layer that solves a quadratic program, say, you can just set up a quadratic program in PyTorch. So that's those first bunch of random lines there. And then you call this QP function with where you pass in the parameters to this program. Of course, those inputs can also be functions of anything else that you want. They're all just tensors here. And then you define some loss as a function of the output of that program. And then you call loss.backwards, and you get all the gradients you want. So everything you want to differentiate through, you can just do it. Now, that requires us to work out how to compute those derivatives there. But now that it's there, anyone can just do it. And in fact, we have this package called qpth, which actually does this very efficiently in a few ways. So first of all, it uses it's a batch solver, which uses GPU-based methods for solving the factorizations of each matrix here in parallel. And one very cool thing, which I won't get into here, but which is really nice about this formalism, is that you actually get backprop to these models for free. And what I mean by that is the computational cost of computing a solution requires you to invert a certain matrix or factor a certain matrix. And when you've done that, you actually can get your backpropagation path essentially for free. So it costs you nothing more to differentiate through an optimization problem as it costs you to actually solve it in the first place, which is really nice. It means we can actually not only solve problems like this, but also get gradients through them and train them to solve certain problems we have. So let me just now review a few of the tasks we've actually applied this to, because of course this is all very abstract right now. And I want to just give a few highlights of the things we've actually done here, but mainly referring to some of the papers that actually did this in them. So in the original paper we wrote on OpNet, we applied it to, amongst other things, solving Sudoku problems. So it turns out Sudoku, while being a very simple task in a lot of ways, is actually quite hard for deep networks to solve because the solution to a Sudoku problem involves global constraints over the output space. However, this can be very easily solved with an optimization problem. And in our example, we show we can actually learn how to solve Sudoku just from input-output pairs. We've applied it also to a little bit more practical task of things like power system scheduling. So we've looked at how to learn dynamics models, which are not sort of good in their own right, maybe, but which are finally used in the loop of some larger system that actually solves an optimization problem to schedule power in an electrical grid. We recently used this to learn zero-sum games. This is sort of a domain called sometimes inverse game theory. But basically, by looking at two agents playing a game, you can actually infer the payoff structure of that game. We've applied it to differentiable physics. So physics engines are a very common thing. If you're observing physical bodies acting, you might want to fit a physics model to that. And we've built a differentiable physics engine, which includes collisions and all these kind of things that are typically thought of as hard to model, while still being able to differentiate through it and basically plug it in as a layer of a deep network. And finally, actually released today, Brandon was posting this now, so it's also going to be out this year at NIPS, we have a differentiable NPC module, which NPC, for those who don't know, it actually is very similar to that problem I showed at the beginning of planning of a car planner, where you want to plan a sequence of states and actions to accomplish some task. In this case, though, we're actually able to differentiate through it to use it in the context of imitation learning or deep learning or deep RL, while having a very nice policy class that is still differentiable and can be sort of treated as a black box within a deep RL loop. So these are all sort of examples of what you can do with these things. But at a high level, what I'm really excited about, and what really excites me about PyTorch in general, is just how easy it is to make these very complex layers, make things which we think of as being very complex sort of units of computation, which once you've built them, can just be plugged into a larger system so that we gain the benefits from end-to-end training, while we also have the modularity, the debuggability of traditional programming. If you want to learn more about this, we have a bunch of code packages released for different aspects of this problem. And I would also really encourage you to check out Brandon's poster. He's giving a poster on this tonight. And I think the last one here he just released today, the MPC version. But check out this poster, and I hope you can build upon these things and find them useful in your own work. Thanks very much.
Hi, everyone. I'm Nargis Razavian, and I'm a faculty at NYU Langone Medical Center. And my background is actually computer science, but my group is primarily between Center for Data Science graduate students and medical school. And this is a work that we just recently presented at Machine Learning for Healthcare. And Yingshu and Zach have done most of the work. Kudos to them. So in my group, and actually now at medical school, I focus on, in a very large medical institute, looking at what are the gaps currently in healthcare, and what are the opportunities for machine learning, data science, deep learning to try to cover as many gaps as possible. In short way, we could say we hope to save lives. And in order to do that, in the past couple of years, the past 2 years that I have been at medical school, some of the opportunities are emerging, and one of them is early detection. So why does it matter so much? If we look at the causes of death statistics from Center for Disease Control, in 2016, for example, more than 65% of deaths are attributed to, you can see the list here, heart disease, cancer, some common chronic conditions. So some of these conditions, if they are detected early, they actually do not lead to death or early loss of life or quality of life degradation. And some other ones, for example, Alzheimer, currently there is no cure for it. But in order to develop that cure, what needs to happen is that that drug needs to be given to patients before they are late stage. That's the reason all the treatments have failed so far. We are detecting and reaching out too late. So there are numerous benefits to early detection. And fortunately, at NYU Medical School, there is a really great initiative to try to, if we can tell them what's going to happen, there are some teams that are ready to go out and find that person and do something. So that's what we do as part of our research. And we look at one opportunity that has emerged, and I will tell you a little about what it is. But we basically, first of all, we try to address as many diseases as possible into the future, diseases that haven't happened yet, but they're probably going to happen soon. And we are looking at some source of data that is, it's called electronic health records. It's been only about a decade that this data is accumulating in somewhat standard format in scale of millions in the US. So New York City is a diverse, huge city, actually. So that means that we do have, we service a lot of patients at NYU Medical School. So for example, in the past 5 years, we have been servicing 6.5 million patients. So I have gone to NYU for my visits. So every time I go to the visit, that's what EHR is. There will be, that visit is called an encounter. If there is a symptom or something, it's recorded. If there's a disease, it's recorded with the timestamp. If there's a lab value, it's recorded. If for some reason I need to have an imaging, it's in the system. So if I'm prescribed medications, it's all in the system. Every single visit is accompanied with a note, which is natural language. And if you think that doctors' handwriting is hard to read, wait and read how they type. So it's the nature of recording. It's, the information content has to be extremely high. They don't have too much time to even write the whole word. They abbreviate, they drop the grammar. It doesn't matter as long as they can quickly document it. So it has its own specific challenges, just the text. So so far we have about 90 million visits. And they are accompanied with more than 1 million different aspects of health, images, time series, lab values, notes. This is incredibly valuable source, and it's only the past 10 years, actually, since 2008, that this is scaling up so much. So since we have time series, we also have access to future of the past. So that allows us to think about a lot of this is a very a simplification that I would say, but many supervised learning techniques immediately are applicable, at least in the first level, to healthcare problems. Because we have time, we look at a range of data. For example, here, like let's say the history window, we can look at any source of data that we have within that window, and we get our labels from the future in that time series. And once we train that model to look at the data and to predict the future, then we can apply it today, and then that's going to give us, what's going to happen in 2019, right? So that's the framework, and the data is noisy, but at very large scale, this is going to create some valuable insights. So we are looking into that, and this work that we recently published looks at a very short-term, 3 to 9 months window, and particularly we are looking at 3 diseases that we have teams at NYU to try to go out and do something for them, and that's congestive heart failure, kidney failure, and stroke. So usually you originally start with very large data, but in order to clean the data, make sure that you have the ground truth in the future, and you have enough data, it does shrink. So our 6 million population shrinks to about 300,000 time series that all fit the criteria to be able to be used in training and testing and validation. So, so now another challenge in electronic health record I may have mentioned is that we have different modalities. So this work in particular not only looks at the structured data, it's in time series, it's very valuable. We also look at the notes, because that is where the information goes. That is where the doctor reviews quickly to see what's up with the patient. And many times, items are dropped from the structured data, but they are in the notes. So that kind of differentiates our group's work from a lot of other work. And one thing that I can mention is that even in machine translation or a lot of great NLP work, which is inspiring most of our work, the amount of the information content that is in those domains is not always the same as information content that's in medical field. If there's a number written in medicine, in a medical note, it matters. It needs to be really, be part of the decision. So that was part of the contribution that we have. And of course, these methods are all generalizable. They are completely scalable to all diseases as long as we have enough data for them. So one thing that is, of course, this is PyTorch developer conference, so let me say kudos to developers of PyTorch, because that's what we use, and it has made a lot of difference. We have developed quite a number of different good existing baselines. We haven't even tried all of them yet, but to pay forward what we got from the community, we also open source everything we are producing in our own research. We are also open sourcing our embeddings. We push as far as our sensitive data allows us, which is open sourcing the models, embeddings, anything that we can, so that this work can impact hopefully more institutes. So one thing that I can mention that is a little bit more important in medical field, which we have to look at, is that we develop the models, but we can't stick to the black box model. Every model decision is questioned by somebody. It's either a patient who's going to ask, why, doctor? Why are you telling me? Or it's a doctor who is going to ask, why am I doing this to the patient? Right? So visualizing black box is actually quite important in medicine. And so we have started to look into various methods, gradient-based methods, which are part of visualization of deep learning models. And and we have invented some other methods, logout-based methods, which are all part of the poster which Zach is presenting. So just as I mentioned, we pass forward. All our tools are open source, and you can find them in this GitHub repository. You can contribute to them. You can use them, leave issues, open issues, everything. And all the details of the paper is also in the archive. So yeah, come to the poster, talk, get engaged, and use this in your groups and communities. Thank you.
OK, we are running about 10 minutes late, which is actually not too bad. So we're going to take 15 minutes, grab a coffee, and meet back here, and we'll start the industry lab section. Thanks.